A 336 aluminum conductor steel reinforced ACSR conductor has a rating of 397 MVA, which stands for megavolt amperes. MVA is a unit used to express the apparent power in an alternating current AC electrical system. It represents the total power flowing in the circuit, including both the real power, which performs work, and the reactive power, which does not perform work but is necessary for the operation of certain electrical equipment. The MVA rating of a conductor is the maximum apparent power that the conductor can safely carry without exceeding its temperature limits or causing damage to the conductor itself or surrounding equipment. The MVA rating depends on several factors, including the conductor size, material, construction, ambient temperature, wind speed, and the allowable temperature rise. ACSR conductors are commonly used in overhead power transmission lines because they offer a good balance of strength and conductivity. They consist of a core of steel strands for strength and an outer layer of aluminum strands for conductivity. The steel core provides the necessary tensile strength to support the weight of the conductor and withstand mechanical stresses, while the aluminum strands provide a low resistance path for the flow of electrical current. The 336 designation refers to the approximate cross-sectional area of the aluminum strands in thousands of circular mils. A circular mil is a unit of area equal to the area of a circle with a diameter of 1 mil, which is 1/1000th of an inch. The larger the cross-sectional area of the aluminum strands, the lower the resistance of the conductor and the higher its current carrying capacity. The MVA rating of a 336 ACSR conductor can vary depending on the specific operating conditions and the assumptions used in the calculations. However, a typical value for the MVA rating of a 336 ACSR conductor is around 397 MVA. This means that the conductor can safely carry an apparent power of 397 million volt amperes. The actual current carrying capacity of the conductor depends on the voltage at which the power is being transmitted. For example, at a voltage of 115 kV, the 336 ACSR conductor can carry a current of approximately 2000 amps. At a voltage of 230 kV, the conductor can carry a current of approximately 1000 amps. It is important to note that the MVA rating of a conductor is a theoretical value that is based on certain assumptions. In practice, the actual power carrying capacity of the conductor may be low due to factors such as ambient temperature, wind speed, and the presence of other conductors or equipment nearby. Therefore, it is essential to consult with a qualified electrical engineer to determine the appropriate conductor size and rating for a specific application. The calculation of the MVA rating involves several steps. Firstly, determining the ampacity of the conductor, which is the maximum current it can carry continuously under specified conditions. This is typically found in tables provided by organizations like the National Electrical Code, NEC, or the Insulated Cable Engineers Association, ISA. These tables consider factors like conductor material, size, insulation type, and ambient temperature. Secondly, determine the voltage level at which the conductor will operate. This is a critical parameter as it directly impacts the power transmission capability. Thirdly, calculating the apparent power using the formula MVA equals voltage in kilovolts times current in amps divided by 1000. This formula directly relates voltage and current to the apparent power. Factors influencing the MVA rating include the conductor temperature. Higher temperatures increase resistance, reducing ampacity and MVA rating. Ambient temperature plays a role as higher ambient temperatures reduce the conductor's ability to dissipate heat, lowering its ampacity. Wind speed also affects it because higher wind speeds increase convective cooling, improving ampacity. The presence of nearby heat sources can also influence the MVA rating because they can raise the conductor temperature, reducing ampacity. Conductor spacing can influence the rating as well. Closer spacing reduces heat dissipation. Understanding these factors is crucial for designing safer and efficient power transmission systems. It's important to select conductors with appropriate MVA ratings to prevent overheating, sag, and potential failures. The NEC provides guidelines for conductor selection based on ampacity and application. The IC also offers standards and guidelines for conductor performance and testing. Consulting with electrical engineers and referring to industry standards ensures proper conductor selection and safe operation of electrical systems. Different types of conductors exist, each with varying MVA ratings based on their material, size, and construction. Copper conductors generally have higher ampacity than aluminum conductors for the same size. ACSR conductors, with their steel core, offer a good balance of strength and ampacity for overhead transmission lines. Understanding the properties of different conductor types helps in selecting the most suitable option for a given application. The MVA rating is crucial in power system planning for several reasons. Firstly, capacity planning ensures the selected conductors can handle the anticipated load growth. Secondly, voltage regulation to maintain voltage levels within acceptable limits. Thirdly, stability analysis to ensure the system remains stable under various operating conditions. Fourthly, protection coordination so protection devices can operate properly without causing unnecessary outages. Ignoring MVA ratings can lead to serious consequences, like overloading conductors causing them to overheat and sag, potentially leading to contact with other objects or the ground. Another consequence is voltage drops, which can affect the performance of equipment connected to the grid. Ignoring it can also lead to system instability, which can result in power outages. Furthermore, premature equipment failure, which shortens the lifespan of electrical equipment due to overheating and stress. Practical applications of MVA ratings are numerous. Firstly, transmission line designed to select conductors for long-distance power transmission. Secondly, substation designed to choose equipment that can handle the incoming and outgoing power flow. Thirdly, distribution system planning to ensure adequate capacity for local power delivery. Fourthly, industrial facility designed to select conductors and equipment for various loads. Fifthly, renewable energy integration to connect solar and wind farms to the grid. Regular inspection and maintenance are essential to ensure conductors operate safely and reliably throughout their lifespan. This includes visual inspections to identify any signs of damage or corrosion, infrared scanning to detect hotspots indicating overheating, tension checks to ensure proper sag and clearance, cleaning to remove contaminants that can reduce ampacity, replacement of damaged or deteriorated conductors. Safety considerations when working with high-voltage conductors are paramount. This includes maintaining safe clearance distances, using appropriate personal protective equipment (PPE) such as insulated gloves and clothing, following lockout-tagout procedures to de-energize equipment before working on it, proper grounding to prevent electrical shock, training on safe work practices. The MVA rating of a 336 ACSR conductor is an important parameter that must be considered in the design and operation of electrical power systems. By understanding the factors that affect the MVA rating and following safe work practices, engineers and technicians can ensure the reliable and safe delivery of electrical power.